Bonjour and welcome to these office hours for week 4 for this class on functional analysis. One of the perks of doing a MOOC is that you can hold your office hours anywhere you want. You don't have to be in your office, and today I am somewhere in Paris. Some of you might actually know the location or figure out the location. If you do, then you will get some brownie points. These brownie points will not count toward the final grade, unfortunately, though. So this is week 4, which means that we are in the middle of the class. I mean, we've passed a lot of stuff. And we are ahead for some new stuff. And what I would like to do today in these office hours is kind of see where we've been, where we are, and where we're going to. And let me start with where we are. A few hours ago, we just posted the videos for week 5. And you will see in these videos that there is a result called the Lax-Milgram lemma that will help proving that equations have a solution and a unique solution, actually. One solution and one solution only. This result will also help us prove that the solution depends continuously of the data. Now, this Lax-Milgram lemma will require some properties on the spaces and the functions to work. We will need to be in the setting of the Hilbert spaces and to have a function on the right-hand side that is in the dual space of this Hilbert space. So you see what we've been doing this week in week 4 is quite useful. Having an inner product, having these Hilbert spaces completeness is the right setting to basically set up equations and look at the situation if they have solutions or not. So you see it's very useful. And also another thing which is useful is that often we are able to bound the norm of a sequence. When I'm saying bound the norm, so that means that we are in the norm space, see week 2. So we bound the norm of a sequence, and from that, from this, we can actually deduce that we have a converging subsequence. Or let me actually rephrase: we have a subsequence that converges weakly towards something. And you see that that means that we have to deal with weak convergence sometimes. Weak convergence, as you know, is not as strong as a strong convergence. This is why it's called weak convergence to begin with. But it is very useful because often we don't have the strong convergence. So we have weak convergence and we just have to be satisfied with what we have. Often we also have weak convergence as a step to the proof of the strong convergence. So you start proving the weak convergence, you get an element that the subsequence or sequence converges to, and you actually do a second half of the proof. You prove that the sequence converges strongly. And this is something that we will address at some point in week 7. We will see that in some cases we can go from weak convergence to strong convergence, and we have the weak convergence in one space, and we can deduce the strong convergence in another space. So this is something that we will see in week 7. And back to what we've been doing so far and what we've done, you see, when we talk about weak convergence, we mean convergence in a different topology. So you see, we started this class with topologies, topological spaces, and you see it's useful to have different types of topologies because sometimes we need different convergences for the reasons we just said. So you see, week 1 we did topology, we did convergences. Week 2 we dealt with metric spaces and norm spaces. And week 3 and 4 we dealt with Banach spaces and Hilbert spaces. And as you can see in week 5, it is useful to prove existence and uniqueness to some equations. Now in week 6, we will learn a lot about LP spaces. These LP spaces that we have defined earlier, we will look into the properties of these spaces. Well, in these LP spaces, which ones or which one is a Hilbert space? Of course, it's useful to know because if we want to apply Lax-Milgram, we might have to know. We will also see the other properties of these LP spaces. What is their dual space? Also, what is the situation when it comes to reflexivity? What is the situation when it comes to having C infinity 0 dense in these spaces? And let me explain here what I mean by C infinity 0. C infinity 0 is the space of functions that can be differentiated as many times as I want, and the 0 in the bottom means compact support, which means the function is 0 outside of the compact set. Now, if this set C infinity 0 is dense in some or all LP spaces, it will help to prove some results, because it means that I can approximate a function in LP by a function which is extremely smooth because it can be differentiated as many times as I want, and it is 0 outside of the compact set. So that is also something we'll look into in week 6. Week 7 will be devoted to what we call Sobolev spaces. And you will see that, again, some of them will be Hilbert spaces, and that is useful in the context we mentioned. We will also define new type of differentiation, and that will help us. You will see that in one of the example for lax minogram this week, at some point we're stuck, or we're not completely stuck, but kind of, well, actually we are stuck, and we have to have a new type of differentiation, and that will be defined in week 7 when we actually work with these Sobolev spaces. And also you will see that some spaces will be included in some others, and again, when we have a weak convergence in one space, sometimes we will be able to derive the strong convergence in another space, and that will be extremely useful. And week 8, we will start with a physical model, find the equations for the model, so basically the model problem, find the equations. We will see that the equations have one solution, and one solution only. Maybe will we be using the Lax-Milgram lemma? I don't want to spill the beans just yet. And we will go all the way to approximating the solution. We'll actually use numerical simulation to find the approximation of the solution. So that's week 8. So you see there is a lot coming up, a lot of interesting stuff coming up. I hope that you will be hanging on, and I really suggest that you keep working on the material. It's really some very interesting material that we will be using in week 6, 7, and 8. So please hang on in there. Before we end these office hours, I would like to mention 2 things on the forum. The first thing I would like to mention on the forum is a thread called I'm Lost Since Week 4, which the title is pretty funny, or maybe not that funny, but what I would like to say is that this thread is actually very interesting, and I would like to point it out so you read it. There is some good material and some good posts and replies, so I suggest that you look at it. Secondly, I would like to also answer one of the questions that was asked in the forum, that regards the bracket notations. And someone asked what was the story, because obviously, it's different in the Hilbert space and Banach space. So let me just re-explain this. If you're in the Hilbert space, the bracket notations means the inner product. UV is simply the inner product of U and V, where U and V are in the Hilbert space, say X. Okay? So that's the inner product. Now, if X is not a Hilbert space, but just a Banach space which is not a Hilbert space, you can still use the bracket notation. In this case, it means the duality bracket. So UV will stand for U applied to V, where U is an element of X star, the dual space of X. So it is a linear continuous function going from X to R, and so U is going to be there. V is going to be in the space X, and bracket UV means U applied to V. And that's a real number because U goes from X to R. Or if you don't like the notations with U and V, just use F and V. So F is in X star, V is in V. V is in X. So F is in X star, V is in X, and FV, the duality bracket is simply F applied to V. Now, if you are in a Hilbert space, as you know, which is also going to be a Banach space, then you have both notations, the duality bracket and the inner product, and they just coincide. I mean, they're just the same thing. Thanks to the Riesz representation theorem, UV is the inner product. It is also the duality bracket because you can identify space X with X star when you are in a Hilbert space. So you see the whole thing is consistent. Okay, so this is the end of these office hours. Before we break, I would like to remind you that we strongly suggest and encourage you to post questions on the forum, answer things in the forum, and be very active on the forum. That's really part of this class. Of course, you are not supposed and you are asked to refrain from discussing quiz questions that are in session on the forum. That is a Coursera Honor violation if you do this, so please don't do it. And as always, I strongly suggest that you submit your homework on time, which means by Sunday night. Paris time, so be careful if you are in a different time zone. And finally, as always, I suggest that you follow me on Twitter. My call sign is @Cagnol, and I will post there some announcements, information, sometimes information about math, Central Paris, or simply Paris. I suggest you follow me on Twitter, and I will wish you a very good week, and I will see you next week.